Welcome to the first video on Green channel. The Green channel aims to publish informative presentation and videos related to various components of the Sustainable Development Goals. This introductory video presentation is one among the series titled Urban Sanitation. It talks about various components of sanitation within the built environment for a better understanding of the subject. The wastewater treatment system deals with conveyance and treatment. There are two basic approaches to wastewater treatment system based on conveyance, which are centralized and decentralized wastewater treatment system. Generally, during the implementation stage, based on wastewater generated at the current, also the future stages and terrain, as well as other social and economic factors, decide whether to opt for a centralized or decentralized treatment system. Often the decentralized treatment system is opted wherein it is too costly, too complex, or too time-consuming, and the connection to a centralized sewer system is not feasible in near future. Considering the cities of the future, which will be water-wise and shall opt for a regenerative water, the focus is to reduce, reuse, and recycle wastewater, wherein fit-for-purpose water and treatment technology depend on options. The options available are based on scale of treatment at building or neighborhood level, proximity of the source of treatment, and possibility of on-site water reuse. The wastewater treatment system based on treatment can broadly be categorized as aerobic treatment, anaerobic treatment, and fecal sludge management. The conventional treatment technology for an aerobic process in principle use activated sludge process. As shown in the figure below, it consists of two major components which are the reactor and the clarifier. The reactor is continuously mixed and aerated. The reactor receives the influent wastewater and activated sludge from the clarifier. The activated sludge from the reactor is settled in clarifier wherein the treated water is carried out in the form of effluent and settled sludge is recirculated to the reactor. During the treatment process, where the redox potential is low, an anaerobic treatment is employed. There are also low energy systems which in principle use anaerobic digestion as secondary treatment such as anaerobic filter, anaerobic baffle reactor, upflow anaerobic slush blanket, etc. And also require tertiary treatment such as constructed wetlands, polishing pond as per site requirement or environmental conditions. They mainly release methane and carbon dioxide in gaseous form. The effluent liquid contains ammonia, phosphates, and other nutrients, which are generally treated by tertiary treatment based on site requirements. The cornerstone to domestic wastewater treatment, which is fecal sludge management, can now be categorized as separate technology, with a focus on maximum reuse of water and nutrient recovery. The fecal sludge management employ various steps such as containment, emptying, transport, treatment, recycle/reuse to extract value and contain pollutant from the backwater. Domestic wastewater consists of grey water and black water, urine/feces, wherein black water is the major source of nutrient recovery which comes under the scope of fecal sludge management. The technical options based on aerobic process, anaerobic process, and fecal sludge management depend on space availability, potential for effluent reuse, budget, conveyance option available, and source segregation. Operation and maintenance play a vital role wherein cost, required skill sets, and managing the byproducts such as sludge is also important. The images shown are the various treatment technology for different options based on technical, social, and environmental factors. Comparing two relevant processes for domestic wastewater treatment, that is activated sludge process and anaerobic digestion, based on the fate of carbon and energy is shown in the figure. For every 100 kg treated aerobically, 30 to 60 kg of sludge is produced, leading to 10 to 12 kg of COD in the effluent. Whereas anaerobic process converts COD into gaseous form with 40 to 45 meter cube biogas and 5 kg of sludge as COD while releasing nutrients and 10 to 20 kg of COD effluent. Considering the microbial growth reaction which feed on organic carbon source and inorganic carbon source, majority of the organism in aerobic process are aerobic heterotrophs. whereas anaerobic process consists of four stages. In the initial stage of anaerobic process, the carbon source is organic, which is fed by fermenting organism, whereas later the carbon source is inorganic, fed by hydrogenotropic methanogens. Other organism fed by organic and inorganic carbon source is shown in the figure. The metabolism of this organism is combination of catabolism and anabolism. The catabolism is an energy yielding process from energy source in the form of heat and stored in the form of ATP and ADP by releasing metabolic products. Whereas anabolism is a biosynthetic metabolism creating bacterial biocells, biopolymers, utilizing energy through conversion from ATP to ADP while consuming external nutrients and creating intracellular precursor pools. The energy scale for redox couple of catabolism for different organisms in treatment process with glucose as electron donor is shown in the figure. The aerobic process requires the most energy for catabolism to occur, whereas for anaerobic process requires the least, as shown in the figure. The wastewater characterization on various parameters such as COD, total kgl nitrogen, ammonia of the filtered and unfiltered effluent and effluent of each process, as well as nitrogen nitrite, nitrogen nitrate, total phosphorus, and phosphates play an important role to define engineering conditions. Where only oxygen is there, an electron acceptor aerobic condition exists. Similarly, where only nitrate is present, an oxide persists. And for anaerobic condition, no oxygen and nitrate should be present.